Let's talk about NMR spectroscopy. NMR spectroscopy is a lot better than infrared in my opinion because instead of just getting what functional groups are in our molecule, we can get what is our molecule exactly. We can have a chemical formula, like a very condensed one, like C something, H something, O something, and we can have a spectrum and we can get our structure. So there are two types of NMR spectroscopy that you probably have to learn, and those are 1H-NMR and 13C NMR. And why is it 1H and 13C instead of like 2H or 12C? Well, because NMR, nuclear magnetic resonance, depends on the fact that nuclei with odd number mass are going to have this innate property of they are going to spin. And so because we're in organic chemistry and our main elements are carbon and hydrogen, we are going to use those elements to figure out what is going on in our molecule by having them spin, and we're going to apply an external magnetic field, and we're going to measure some differences that happen. Proton NMR is generally, or 1H NMR is generally a lot more useful. You can get a lot more out of it than carbon NMR because you can have hydrogens not only on carbons but on heteroatoms like oxygen, nitrogen, etc. So what we're doing is when this nucleus spins, this hydrogen nucleus, we're dealing with hydrogen nuclei only for this whole entire 1H NMR thing, it's going to create a magnetic field, kind of like a loop of wire with a current in it, for any of you who've done like electronics and magnetics and physics. So what we can do is we can apply an external magnetic field and look at the change in energy that happens when the proton is splitting itself between two different states, or when it's going between two different states, the energy favorable one or the less energy favorable one. And so here's kind of an illustration picturing the proton, the spinning proton, as a bar magnet, like the kind that has like a north pole and a south pole, because basically that's what's going on. And so these protons are all going to be in different positions to begin with, but they're going to align themselves depending on the magnetic field, and that's going to drop their energy to a certain amount. And we might be thinking, okay, so all the protons drop energy, they all drop the same energy because they're all protons. Not necessarily true, because electron density can shield this nucleus from the effect of the external magnetic field, and then it doesn't have to expend as much energy, or it doesn't have as much of a difference in energy when it aligns with that magnetic field. And this is based on something called de-shielding. So if electrons shield you as a proton, then de-shielding is when electron density is withdrawn from where our protons are. So for example, look at this N-butyl bromide. Each consecutive carbon has less of a de-shielding effect from the more electronegative bromine. So this bromine is withdrawing electron density, and these protons right next to bromine on this carbon are getting lots of inductive effects from bromine, and they're not going to have as much electron density on them, which means that the magnets in the NMR can exert more of an effect on them. The ones that are farther away, not so much, and this is going to result in a difference of signals on the spectrum. And this can be seen in our spectrum. Our spectrum goes from about 1 to 10 parts per million. Parts per million is just our way of measuring this. And you can see here a spectrum of methanol. And methanol has got two types of hydrogens. So the concept of types of hydrogens is because since these three hydrogens are all bonded to the same carbon, they all have the same relationship with everything else in the molecule. They're equivalent hydrogens. So they're not going to produce three signals, they're going to produce one signal. And then the other H is going to produce a second signal. So in methanol, because we only have two types of hydrogens, even though we have 4 hydrogens total, we're going to see 2 signals on our 1H NMR. And the signal for the H that's attached to the O is going to be more de-shielded, which means it's going to get a higher number on the spectrum. It's going to be more to the left. Spectra are backwards the way, NMR spectra are backwards the way that infrared spectra are backwards, in that they count up to the left. So it's like a reverse number line. But anyways, so the H that is attached to the electronegative oxygen, that is going to be more de-shielded and it's going to get a higher signal. Whereas the other H's are going to be less de-shielded. I know we can just say more shielded, but people don't say that. We say less de-shielded because the de-shielding is what we care about, and that's what's actively going on. So those guys are less de-shielded, and they're going to get a lower number. You might also notice something where this peak is shorter than that peak. This is called integration. So this spectrum, or the spectrometer, it can actually kind of tell how many hydrogens are on each atom, and it can put all the equivalent hydrogens with the height of the peak, and the higher the peak, the more equivalent hydrogens there are. And when you see these spectra for real, this is kind of a bit of a simplified fake spectrum. When you see them for real, they're probably going to tell you the number of hydrogens, because you don't want to do like a measurement on here and say, okay, this is 1/3 as much, because you can see it's not even, doesn't even look like a third. So they're going to tell you. But that's chemical shift, and there's a ton of different common signals that we see. So alkanes are going to be the least deshielded. Nothing's going on with them. There's no electronegative element. If you have one that's farther in, like if you have a CH3, CH2, the CH2 is actually more deshielded because of London dispersion forces. If you continue on and you have a carbon that has more bonds, this hydrogen is going to be even more deshielded. So the nearer you are to stuff, the more deshielded you are. As you get to have some interesting elements, you're going to have more deshielding. So for example, this methyl ketone is going to have more deshielded stuff because it's near an oxygen. If you're bonded to a carbon that's bonded to a halogen, even more deshielded. And then we have double bonds. Those are also going to be deshielded. Benzenes are a whole nother thing. Apparently, somehow, the electrons in benzene, that like complex of attached p orbitals that we always talk about when we talk about benzene, will make the electrons go in such a way that it actually goes with the magnetic field, the external magnetic field. And so that's deshielding kind of indirectly. And then there's a couple groups that are way out there. Aldehyde and carboxylic acid are in their whole own world at like 9 or 10 or 11 parts per million. Alcohols are actually going to be less deshielded than that. So, like, I know that's weird that an aldehyde hydrogen, which is bonded to a carbon, is more deshielded than an alcohol hydrogen that's bonded to an oxygen, but that's just the way it is. So alcohols are going to be like 4, 5. They've got a pretty broad range, but you'll be able to tell from the formula and from other stuff that we're going to talk about where they are. And then amines also deshielded. So this is another example of how shielding can work and deshielding. So the benzene hydrogens are more deshielded than the methyl hydrogens, but the methyl hydrogens are also deshielded by the fact that benzene is there bonded to them. Now, one thing I forgot to mention is what the heck are we comparing all of this to? Well, our kind of control group is going to be something called TMS, or tetramethylsilane. Silicon is in the same column in the periodic table as carbon, and so these methyls are going to be bonded to silicon, which is less electronegative than carbon. And since it's less electronegative than carbon, these methyls are going to have more electron density. They're going to withdraw electron density from silicon. And so the hydrogens in those methyls are going to be more shielded or less deshielded than anything we're going to see in organic chemistry where silicon doesn't really play a role. So that's kind of our control. This is TMS. This is not one of our hydrogen peaks. So here are some more examples just to get you used to the NMR spectra. We've got a methyl ketone, and that is characteristically around like 2.1. Although these things aren't exact, like if it's 2.2 or if it's 1.9, it could still be the same kind of functional group. You can also see all these methyl hydrogens are all equivalent because of symmetry, because they're all bonded to the same thing and they have the same relationship to everything else in the molecule. They're all going to be grouped together, all 9 of them. And then these guys are deshielded because they're closer to the oxygen than all those other methyl hydrogens. And then we can continue and look at this compound. This is an ester. So notice that the ester, you have this carbonyl with no hydrogens. Here, there's no hydrogens. So that's not really deshielding things as much as if it were an aldehyde or a carboxylic acid. But we do see some of these groups that are deshielded, like this methyl is next to a ketone, and so that's going to be deshielded. These are between two ketones, so those are going to be the most deshielded compared to the one that's next to one ketone. And then these guys are farther away from all the oxygens, and so they're going to be the least deshielded. There's also this benzene. What's on this benzene? It's a orthomethyltoluene. So these methyls are going to be kind of equivalent to each other because they have the same relationship with everything else in the compound. So that's one kind of hydrogen, and then these guys are another kind, and then these guys are another kind. But this introduces a concept that you're going to see that, like, sometimes, even though some hydrogens on benzene are technically different, like this is not the same as this because one of them is closer to the methyl than the other, they're kind of going to be grouped together. Sometimes you can differentiate them. Like if you have two substituents on your benzene and one of them is electron withdrawing and one of them is electron donating, then you can differentiate them. Sometimes with this one, not so much. And then this is just an example of how integration works that I put in. So, what's next? Well, we can consider what's called splitting. And this is going to help us a whole lot. It's kind of complicated, but it helps us a lot because here's how it works. So, if you are a hydrogen and you are on something that is on something else that is next to other hydrogens, so the hydrogens are like one carbon or oxygen or nitrogen or whatever away, you're going to have something called spin-spin splitting. So the spinning of one hydrogen nucleus is going to affect the spinning of its neighbors. And so what that gives us is a pattern where we get more than one signal in the one signal for that one group of hydrogens. So for example here, the two hydrogens that are circled in pink are next to one other non-equivalent hydrogen neighbor. Notice I said non-equivalent because if I had these guys are equivalent hydrogen neighbors and would not split each other. But non-equivalent hydrogen neighbors are going to split. So you see how you get two peaks here? These are part of the same signal. They're super zoomed in, but they are two peaks. And so the rule that we use is called n+1. So if I have one non-equivalent hydrogen neighbor, then I am split in two, and it's called a doublet. If I have no non-equivalent hydrogen neighbors, my n is 0, and I'm going to have one peak or a singlet. If I'm next to 3 non-equivalent hydrogen neighbors, then I'm going to have a quadruplet because 3 plus 1 is 4. So for example, a common thing that you're going to see is CH3, CH2. This is an ethyl group. These hydrogens are next to 2 non-equivalent hydrogen neighbors. So that means they're going to have a triplet. And then you're going to see for these guys, they have 3 non-equivalent hydrogen neighbors, so they're going to have a quadruplet, assuming that something here is like not carbon. And so if you see this on a molecule, what's going to happen is these guys are going to be more deshielded because they're in the middle. Bromine doesn't have to be bromine, it can be anything as long as it's not a carbon with hydrogens, or anything with hydrogens. But the point is that the CH2 is going to be more deshielded. So the way that this is going to look for CH3CH2 is that first, on the right, you're going to see your CH3 signal. It's going to be a triplet. And then more deshielded, you're going to see your CH2 signal, which is going to be 2 hydrogens, and it's going to be a quadruplet. And so when you see this enough times, when you see 3 hydrogens triplet and 2 hydrogens quadruplet, you're going to notice that it's an ethyl and you're going to get used to these types of patterns. When we get past like 4, sometimes they will just call it a multiplet instead of going into all these prefixes here. But sometimes it matters and it can help us. So for example, if I draw out this, then this hydrogen has 6 non-equivalent hydrogen neighbors, and so it's going to have n+1, 6 plus 1, it's going to have a septet. And if we get told that, then we might know, okay, it's attached to 6 other hydrogens, that could be 2 methyl groups. So, useful stuff. For example, in this one, here you're going to see 2 hydrogens, and because they have one non-equivalent hydrogen neighbor here, it's going to be N+1, a doublet. So we're going to see like 2 hydrogen doublet, and that's the way that sometimes people abbreviate things. And then this one has 2 non-equivalent neighbors, so it's going to be 1 hydrogen triplet, because 2 + 1 is 3, triplet. And then this one, the 1 hydrogen is more deshielded because of the 2 bromines on that carbon, whereas the other 2 only have 1 bromine on that carbon, which explains the difference in the ppm. So here in this one, we have isopropyl methyl ketone, and which one do you think is going to be the most deshielded? Which group of hydrogens? It's going to be this one, because this one is also next to the ketone, but it hasn't got the other groups around it. Remember, more stuff usually equals more deshielded. So those guys are what I was talking about before, how we have 2 methyls, 6 hydrogens. So it's going to be, we have 2 hydrogens, and it's going to be a septet, because 6 + 2 is 7. So here is our septet. And then these 6 hydrogens are all going to be in the same signal, but actually this one's going to be the next most deshielded. So this is this is going to be this, and these guys are going to be that, because they're the farthest away from the oxygen, from the carbonyl group. And notice that there's no signal for the C or the O, because there's no H's on here. And we have p-nitrotoluene. So in p-nitrotoluene, this is what I was talking about, where if you have 2 different groups and one of them is maybe electron donating, like our methyl, and one of them is maybe electron withdrawing, like our nitro group, which is notoriously very electron withdrawing, then these hydrogens here are going to be different than these hydrogens here. But the ones that I put in the same circle are equivalent to each other. So the ones that are next to the methyl group are going to be less deshielded because it's electron donating, right? And the ones that are next to the nitro group are going to be more deshielded because they have electrons withdrawn from them, and their shield is their electrons. So these hydrogens are going to be in this one, and the splitting is going to be a doublet because, let me erase all my craziness here. Each of these hydrogens, this one and this one, have 1 non-equivalent hydrogen neighbor. So they're going to be in doublets. They're going to be a doublet. And then notice that you don't add them up. So like, because this one has 1 and this one has 1, it's not going to be 2, it's just going to be 1, and then n+1, 1 + 1 is 2. And then these 2 are also going to be a doublet because these ones are 2 carbons away. So if we follow our path, 1, 2, that's too far away. So they're not neighbors. But the ones on the benzene are. So here and there, non-equivalent hydrogen neighbors, each one has 1. So that's going to be 1 + 1 is 2, again a doublet. And then that methyl is going to be an example of a singlet because the only thing that this carbon is attached to is a carbon that's blank and has no hydrogens. So that will be a singlet, 3 hydrogen singlet. Here on the right is a summary of everything we've talked about with deshielding. So we can see all the different groups. We've got alkyl, we've got like methyl ketone is going to be somewhere in here. And then we also have our halogens, our oxygens, allylic, aromatic, and then aldehyde and carboxylic acid is like way out there. The other important thing is usually they're going to give us a formula. So they're going to give you a formula and they're going to give you a spectrum and they're going to expect you to know what the compound is. And it's helpful to know the degrees of unsaturation. The degrees of unsaturation is basically anything that will unsaturate your compound. Unsaturated means that you don't have as many hydrogens. So this is double bond or a cycle. Double bond can be CC double bond, CO double bond, CN double bond, triple bond, which is 2 elements of unsaturation. It can be a benzene. Benzenes, you have a cycle, that's 1 element of unsaturation. Then you have 3 double bonds, which makes it 4. So if your formula says 4 elements of unsaturation or more, probably a benzene in there. How do you get elements of unsaturation or degrees of unsaturation? Same thing. You use this formula that I have pictured up on the top right. So let's try it with this example spectrum with C4H8O2. So notice the O's don't factor into the formula, but we have 1/2 times 2 times the carbons, which is 4, plus 2, plus the nitrogens, which is 0, so I'm not putting it down, minus the hydrogens plus the halogens, but we don't have halogens, so just minus 8, which is the hydrogens. So 2 times 4 is 8, plus 2 is 10, minus 8 is 2, times 1/2 is 1. So whatever this mystery compound is, it has 1 degree of unsaturation. So now let's analyze our signals. So we have at 4 parts per million, it looks like a quadruplet. And then at 2 parts per million, we have a very tall singlet. I know my handwriting is awful, but I'm saying it also. And then we have very shielded or very not de-shielded, we have a triplet. Now this did not give us integration. It did not give us how many hydrogens are at each peak, but we can kind of eyeball it and say that there's not as many at the quadruplet, not as many at the triplet. The triplet's got like an in-between. And then the singlet is more hydrogens. So we've got 3 peaks, and we've got to account for all of this. C4H8O2. So the 3 peaks tells us that either we have things that are in different carbons that are equivalent to each other, or we're going to have carbons or oxygens or whatever that don't have hydrogens on them. And so whenever I see this discrepancy between peaks and the number of carbons or the number of oxygens or whatever, I like to think that we might have a carbonyl, because if we have a carbonyl, then what's going on is we have a carbon that does not have any hydrogens on it, unless it's an aldehyde, but we know it's not an aldehyde because things are absent out here. So we know it's not an aldehyde, we know it's not a carboxylic acid because there's also nothing out here. So these oxygens, they can be an ether, they can be an alcohol, they can be an ester. But because there are 2 groups that are shielded by 1 and 2, and only 1 group that's out like in the 3 to 5 range, I don't think that that it's like a diol or anything. I think it's got to be an ester, because that would incorporate the carbonyl idea, and it would also tell us that we only have like 1 group that's next to an oxygen. So if we put down an ester, just for fun, and that's one element of unsaturation, by the way, is this double bond is an element of unsaturation. Because if we didn't have it, we would have an H on the C and an H on the O, which is saturating. But if we take a look at this, we have a quadruplet and we have a triplet. And the quadruplet is really de-shielded. And so what I'm going to say is, what if the quadruplet is directly bound to this oxygen? Because we have to have something here, and we can't have this bonded to 3 carbons, because then we've used up all our carbons in what goes here. So it's got to be bonded to other stuff. So I'm going to call it a CH2. Because then, if I do a CH3, this is our like triplet and quadruplet thing. Because this is a quadruplet because it's got 3 neighbors, 3 plus 1 is 4. And then the triplet, which is more de-shielded, can be our 2 plus 1. And then we just have a singlet, and the singlet makes sense to go here because these guys have no non-equivalent hydrogen neighbors. The neighbor is here and there's no hydrogens there. It also makes sense that these are more de-shielded than these. So I'm going to label this A and B and C. Okay, so then this would be C, this would be A, and this would be B. So I hope that made sense. I tried to do another one, but then what happened was I ran out of time because this app I use has a limit. So I'm going to cut the video short here, and then I'm going to make a part 2 with worked examples.